Hello, welcome to Microwave and Millimeter Wave Power Amplifiers, Technology, Applications, and Future Trends with Dr. James Komiak. I'm Mike Hamilton, your host for this IEEE Microwave Theory and Technique Society webcast, which is sponsored by National Instruments. Before we start, I'll mention a few housekeeping items. First, this presentation will be archived. A recording should be posted approximately 24 hours after we finish the presentation. We'll send all registrants an email when the archived webinar goes up so you can revisit it or share it with your colleagues. Second, we encourage questions. We'll answer them after the talk, but you can submit them at any time during the discussion. Enter them in the Q&A box on the left side of the webcast window, and don't forget to hit submit. Third, some words about the interface. You can enlarge slides by clicking on the green rectangle at the top right of the slide area. If you're listening over your computer speakers, you can adjust the volume in the media player area at the upper left of the screen. Remember, you may also need to adjust your system's master volume. The icons at the bottom of the webinar window include a file folder. This links to a resource page where you should be able to download copies of the slides. Now let's introduce our speaker. Dr. James Komiak is a BAE Systems Global Engineering and Scientific Fellow. He received a PhD in electrical engineering from Cornell University in 1978. In his graduate research, he developed the real frequency technique for broadband matching of an arbitrary load to a resistive generator. He has 37 years of experience in system, module, and MMIC design for electronic warfare, communication, and radar applications. He has over 100 publications and 13 patents. Dr. Komiak was elected to the grade of IEEE Fellow in 2005 for contributions to monolithic microwave integrated circuits, high-power amplifiers, and transmit-receive modules. And then in 2008, he was inducted into the Association of Old Crows Electronic Warfare Technology Hall of Fame. Dr. Komiak is an IEEE MTTS Distinguished Microwave Lecturer for 2014 to 2016. So now it's my pleasure to turn the virtual podium over to James Komiak for Microwave and Millimeter Wave Power Amplifiers, Technology, Applications, and Future Trends. James?
Thank you, Michael. Can we advance to the first slide, slide number 2? There we go. Okay, enough said about myself. I work for BAE Systems currently, and this presentation is an abridged version of my Distinguished Microwave Lecturer talk. Let's start with slide number 3. Why are power transistors so important? Well, they typically dominate the transmitter and system characteristics. They're the highest in DC power consumption. And what goes along with that is power dissipation and heat. So they're the highest thermal load. They're stressful operating conditions, which impact reliability. The ramifications are high junction and channel temperatures, high DC operating voltages, and large AC signals, all of which are stressing, and cost. Power amplifiers have large chip area, highest chip count. They are low yield, technology intensive processes, highest cost per chip, as well as per area of chip, and they're the largest of MMIC types and have very high periphery, all which have negative impacts on yields. I'm going to first go through the current focus in usage for the transistor technologies that people are focused on using. And the first of those is the current generation of silicon LDMOS. It's based on MOSFET technology. It's low cost, proven performance and reliability. It continuously improves year after year in terms of frequency of operation and thus gain and power add efficiency. and it has a field plate for increased gain as an example, low source inductance using a P-type sinker. It's evolved from MOSFET technology, and so it enjoys the heritage of being silicon technology and extremely low cost. And as I'll show later in an amplifier example, the reason this technology sticks around is the great proven performance and reliability at low cost. Yes, there are devices that are better in terms of the performance metrics, but they're higher cost. So this technology forces designers to think, what am I going after here? Am I going after low cost and adequate performance, or do I really want to pay that extra cost for that extra performance edge? The next device is the gas pseudomorphic Hemp, first demonstrated in '86. Evolution of the MESFET technology. That was the first microwave solid-state field effect transistor. And this technology is ubiquitous. Multiple processes, multiple foundries, multiple sources all over the world. Used for low noise, power, switches, phase shifters, 1 gigahertz to 80 gigahertz. The key to this is you think of it as sort of a designer's profile FET, that rather than a uniform structure, you've got a heterostructure with built-in layers that give you some advantage. In particular, you have the in-gas channel. And typically the indium percentage is between 15 and 30%. Most of the processes are 25 or push the percentage up to 27%. Indium in the channel gives you enhanced electron transport, which gives you higher transconductance, higher gain, higher frequency response. At the same time, we have this conduction band discontinuity that allows higher channel current and allows the carriers to flow in an undoped region. Because that region is undoped, it gets reduced impurity scattering compared to a doped channel device. And because of that, you have improvements in gain, efficiency, and current density. There's another variation. Typically, these are depletion mode devices, but there's an enhancement mode device that was developed for single supply voltage operation for wireless type applications, and it is the principal competitor for the HBT in cell phone type applications. The next device is the indium phosphide Hemp, and this is really pushing it up in frequency. People either use indium phosphide substrates, or there's a variation called metamorphic Hemp, which is the indium phosphide Hemp grown on a gas substrate. With a lattice match device, you can move up to 53% indium, stretch it to 80% pseudomorphic, or all the way to 100% with Hemp technology. Higher indium and higher enhanced transport of electrons, larger conduction band discontinuity, very high current, very high transconductance devices demonstrated. And this is like the device with the highest frequency response that's in use today in terms of solid state, with Fmaxes of 1.5 gigahertz. My rule of thumb is that you can make a very good amplifier to 1/3 of Fmax, and you still can make an acceptable amplifier to 1/2 of Fmax. So we're pushing terahertz type of performance, true terahertz type of performance with this transistor. The downside is the higher indium, and the structure for indium phosphide Hemp gives you low breakdown voltage, which reduces the power density. GaN Hemp. This has become the subject of focus of the industry just about everywhere. It's grown on silicon substrates as a standard due to the DARPA program, which developed the technology. And just about everybody uses silicon carbide nowadays. There's silicon versions, but silicon is not as good thermally, and the transistor doesn't perform as well RF-wise. These devices are thermally limited, and I'll talk about that a little bit later in the presentation. Fmax at 230 gigahertz have been reported, so people use this as an amplifier up to W-band. Now I'm going to take a look at benchmarks, and this is a very busy view graph, but there's only a couple of takeaways and points I want to make on this. If you look at it, all the technologies that are on here tend to be in the same regime in terms of the power added efficiency. And they all tend to be what I like to call wave shaping classes of operation, where you try to get your voltages and currents in quadrature and square them up so the DC current is the lowest and you get the best power added efficiency. And another point I wanted to make is this is all at microwave. You're gain limited at millimeter wave, so you're really forced to be a Class AB1, high bias Class AB, or even Class A. So you don't get these sort of numbers up in millimeter wave. But the point in terms of GaN Hemp is it's in the mix with the best of them. And that doesn't tell the whole story, because GaN runs at a much higher voltage for a given power output and much lower current. So your impedances are higher, your bandwidths will be greater, your matching losses will be less. So there's an additional circuit benefit of GaN technology. I'd also like to emphasize on this view graph that these are little hero devices, very small devices tuned up by a technician or engineer in the laboratory to get the ultimate in performance, and probably the device even went south before the test was over. And that's a lot different than the derating we have to do in the real world to realize a real amplifier. This is how you take that little device shown as intrinsic device at the top and get to the power levels that we need to get to make a real power amplifier. The first thing is you build a bigger power transistor cell. This is the transistor building block that you characterize extensively for your design. You can't go all the way to the peripheries desired for a given power level because it would be unstable and thermally limited and not able to characterize or model it. So you build it up based on a little cell. And you can do that effectively with modern CAD. Then you get to the basic power amplifier, and you've got a choice to make, all the way from a discrete device shown on the left with all matching off-chip to a full mimic, a device on the right with all matching on-chip, or something in between that's a compromise. Usually the next level, you take a number of devices, somewhere between 2 and 8, and power combine them in a module. And at that point, you've got two ways to go. The constrained plumbing route, which is indicative of waveguide, radial type structures, and spatial type of combining on the other side. Both low loss methods of getting to higher power levels. I'm going to talk about the history of circuit design from a historical perspective to tell you about the advances. Advances in power amplifiers have always been coupled with advances in measurement and characterization and modeling technology, as well as circuit design technology, not just transistor technology. So this is where I started out, the prehistory of circuit design. You had a Simpson volt-ohm meter and you had a slide rule. Your models were very, very simple, very crude way to design a power amplifier. The next step and the big advancement was the advent of the automatic network analyzer that allowed you to automate S-parameter measurements. Simulation, the first programmable hand calculators came out, so you could automate some of the process. Models, you can see the model now has losses in it and reactive elements and controlled sources, whereas before all you had controlled sources and diodes in the model. The next advances was the 8510, which really increased the accuracy, flexibility, and speed with which measurements could be taken. The models also appeared with more sophistication, And for the first time, you had commercial simulation tools, although they were linear, that appeared on the market. Up until that point, laboratories and large companies would write their own design software, and their engineers would use that to do designs. So this was really the nexus of the next way of doing power amplifier design in the 80s, but we still didn't have nonlinear analysis. The next step was in the 90s, and here you had simulation tools such as harmonic balance, which allowed you to separate the nonlinear and linear parts of the problem out. So the efficiency of the linear analysis in the circuit simulators could take care of frequency response. And then you would match the voltages and currents at the junctions between the nonlinear elements and the linear elements in the iterative fashion using things such as a Newton-Raphson optimization to converge the two to an answer. So for the first time, we could do real nonlinear simulations using basically a linear tool that is very efficient. Prior to this, you had to resort to time domain simulation, which was very cumbersome. You had to run thousands of RF cycles before you could get to steady state from an initial condition. It was prone to error of interpretation, and it just couldn't fit in the computers of the time. And so this was the big advancement that happened at that point. At the same time, you started to get advances in instrumentation, such as pulse IV, and large signal models started to be developed. In the 2000s to now, you got another advancement with the X parameters on the PNAX, vector signal analysis. The simulation tools took it another step with circuit envelope, and it's now Keysight, but all my view graphs have the historical name of the company when these things were developed in them, rather than going through and updating them. And that took it another step, that you could separate the data rate, which is even slower than the modulation from the RF carrier, and do things like error vector magnitude and calculations like that on modern bandwidth efficient modulations that are used in modern communication systems. The next set of view graphs talk about how through time I personally dealt with the limitations of technology to be able to do state-of-the-art power amplifier design. And this first example is an octave band 10-watt amplifier. It's the first octave band 10-watt amplifier that was ever reported. It's in the MTTS MIMIC historical exhibit. And the methodology there was we only had linear tools. But a colleague of mine, Steve Cripps at the time, had a very insightful observation that the real part of the optimum impedance match for power could be derived from the quiescent currents and voltages of a Class A amplifier. And therefore, just from IDSS, IDS, VDS, you could calculate ROPT. And then the linear versions of the reactances can be used for the other elements, and this determines an approximation to the optimum Class A load. To a certain extent, it also would work for Class A, B, and Class B, although there was some error induced in that process because your voltage and currents aren't really your quiescent. I took it another step and actually put that ROP substitution right into the small signal model in the design of the power amplifier, so I could jump back and forth between quasi-large signal and small signal. And at the time, all we had was load pull measurements, which automated manual tuners, and that gave us optimum load information as a sanity check. Now, this one was my first amplifier designed using a nonlinear model. It used a Gummel-Poon nonlinear model. It's a heterojunction bipolar transistor amplifier. It uses a cascode configuration where you have a common emitter device followed by a common base device. That cascode happens to be very high efficiency, very unilateral, reduced S12 as a combination, and it makes an amplifier that usually has about 1.5 times the gain performance of a single-stage amplifier in the size of a one-stage amplifier. And this one was likewise a state-of-the-art result with about 45% average efficiency across a sub-octave 7 to 11 bandwidth with up to 7 watts of power output. Now we're jumping to closer to where we are today. This is a 10 to 1 bandwidth high power amplifier, 10 watts minimum, that was developed using Hemp. It was originally implemented in dual field plate technology, but we developed a no field plate technology to overcome some of the limitations of on bandwidth and efficiency on this sort of amplifier. And you can see that in this particular case, the comparison to the two is that we got improved performance substantially out of the no field plate device. This is a non-uniform distributed power amplifier, 2 strings. If you look at each string, you'll see 2 things about it. Number one, you get clumping of the devices on the left, and that provides non-uniform periphery. The optimum impedance for those first devices is on the order of several hundred ohms. You can't realize that in microstrip. By clumping devices, you lower the impedances, and so it's non-uniform in periphery. You can also see on the output drain line that it's non-uniform in characteristic impedance in the output network, and there's no termination on the gate line. All techniques to do a non-uniform distributed power amplifier. The bias element is always the bandwidth limiting element on wideband amplifiers. And in this case, it's a spiral inductor that had to be wide enough in its conductors to handle the high currents and still give adequate inductance to meet the low frequency end and minimize the parasitics, shunt capacitance and interwinding capacitance, so it still worked adequately at the high frequency end. Now let's talk about power amplifier advanced architectures. This is where all the publications and research has been lately. For systems such as wireless, where you have a dynamic range of power output that you want to achieve efficiently, there's the techniques of stage bypassing and gate switching. Stage bypassing just gets around your output stage and uses the driving stage as an output stage. Gate switching removes some of your active periphery from contributing to power output. And those are 2 techniques that have been employed for wireless. The CON EER, also called Link, it combines a nonlinear power amplifier, which is your envelope amplifier, and impresses upon it a modulation with a linear drain modulation amplifier to form a high efficiency linear amplifier. Envelope tracking typically dynamically varies supply voltage to conserve power, but follows the signal with sufficient excess headroom to allow the PA to operate near saturation at high efficiency. But like all power amplifiers, it is nonlinear, so it does produce distortion, and I'll talk about that in a bit. Outfacing basically uses signals of time-varying phases to efficiently combine at the output as an instantaneous vector sum to allow the desired signal amplitude. And this has recently received a lot of attention in the literature. Dougherty, you've seen this as a mainstay in publications, both in LDMOS and in GaN. Year after year, we have publications related to various Dougherty amplifier techniques. Wideband, free section, multi-section, unequal size. And in fact, last year at IMS, there was a 1 kilowatt Dougherty amplifier that was reported. Outstanding power level. Now, I'm going to go into some real-world examples here. Now, this is a silicon LDMOS push-pull amplifier. The balunds themselves are very simple. They're ferrite cores with a coax that's wound around it. It's shown on the left in the photograph. The shunt matching elements are these capacitors that go side to side. Because the way a push-pull amplifier works, it's at a virtual ground. So half of those capacitance values appear in shunt as matching elements on the two sides of the amplifier. So here we have an amplifier that puts out over a 4-to-1 bandwidth, 150 watts, about 40% power added efficiency, and you can build it for about $100 worth of parts. Like I mentioned at the beginning with LDMOS, this is one of the reasons why it just sticks around. There's no other technology. If you tried doing this with GaN, yeah, you'd be higher efficiency, but guess what? You'd probably be 3 or 4 times the cost. This S-band GaN Hemp power amplifier, I wanted to illustrate a couple other types of constructions. This is the internally matched FET type of construction using GaN Hemp chips, where you use lumped elements like wire bonds and shunt capacitors and distributed elements like high-K substrates to combine large periphery chips. This is a pulse result, and the reason for that is that in a discrete device like used here, heat flow is only vertical, whereas in a MMIC, it would spread out horizontally in 2 directions. So thermally, the limitations of a GaN Hemp are aggravated even more with a discrete device. It's shown on the evaluation board, which provides the biasing and some additional matching external to the package. This group of researchers actually got this up to a kilowatt in a later publication, but this publication had the photos and it allowed me to talk to the different type of devices, so that's why it's in this presentation. Outstanding result. Now here's, we're jumping to Ka band, and I'm going to compare this amplifier to the previous generation P-amp. This amplifier is a quadrature balanced amplifier, 2-stage amplifier. It's doing about 15 watts power output at about 22-21% power efficiency at this bias point, which is 34 volts. The efficiency goes up, but the power goes down at lower voltages. It's the highest CW power reported at Ka band. It works across about 3 gigahertz of bandwidth. The previous generation was a P-Hemp, and it was single-ended. It had 3 stages to get to the gain. It had larger efficiency. It was only 5 watts, 1/3 the power output, and it was about 19% efficiency. So you can see between the circuit advantages of GaN Hemp compared to P-Hemp that the performance is just superior, which is why it has taken off as displacing P-Hemp power amplifiers through most of the microwave and millimeter wave frequency regime. The next example is a wideband GaN Hemp non-uniform distributed power amplifier, 17 to 40 gigahertz, about 12 watts average across that band. A couple things were done here. It's a 2-mil substrate, which minimizes source inductance and allows realization of lower impedances. It's basically the microwave device, but channel dimensions, source gate and drain spacings are reduced. It has smaller slot vias placed under every source. So although the channel structure is basically the same as the microwave device, you get enhanced Ka band performance out of this device. At W band, this is sort of a dated result. HRL has gotten this chip up to over a watt at this point, but it shows you what can be done, and the reason I left it in here, photo of the chip, measured data, a bit of a description of the chip in the view graph. This is a 3-stage amplifier using 2-to-1 ratios at W band, covering 84 to 95 gigahertz in GaN Hemp. And it's indicative of the type of performance that you can expect with GaN Hemp at W band frequencies. This is the highest reported frequency amplifier. Northrop Grumman reported a terahertz indium phosphide hemp mimics. It's a 10-stage mimic with 9 dB of gain at 1 terahertz. It uses 25 nanometer, that's 0.025 micron indium phosphide hemp. And it's on an 18 micron substrate, less than 1 mil thickness. And it uses a very small cell with only 4 micron finger lengths. CPW mimics, so they avoid the use of via holes altogether to minimize source of inductance. Highest frequency amplifier that's been reported. Now there's other types of power combining that are in between what I described, and I'll just casually mention a couple of those, such as the radial and the spatium that Qorvo has developed. But the real focus I want to focus on is the phased array. And the magic in the phased array is that equation down at the bottom, EIRP, effective isotropic radiated power, which is gain per element times power per element times n squared, where n is the number of elements. So to see the power in this, let me describe just a hypothetical example. It's easy to get to 100-watt type of power amplifiers and GaN mimics. So if you combine 100 of these, even if you have no antenna gain, you're at a 1 megawatt EIRP. That is a serious power level. At the same time, the reason that phased arrays are becoming ubiquitous is you can steer them in a desired direction and use the multi-mode capability of a phased array to do multiple functions. So basically you get spatial and time agility in addition to the power combining. And because of that, you'll find that phased arrays are starting to enter into communications, EW, they're already there with radar, and it's to focus a future system direction in terms of high power. Now, let's take a look at where the benchmarks have moved over the years. I've got a lot of solid-state technologies on here, and I'm showing GaN. I did not include phased arrays or the very high-power tubes, such as gyrotrons, because they would really compress the scale with their megawatt-plus type of power levels. But you can see that GaN Hemp has totally changed the equation in power amplifiers in terms of their performance. There's one exception with the tubes that I have on there, and that's the traveling wave tube amplifier. GaN shows a bit of an inflection point somewhere around 40 gigahertz or so, where its performance rolls off as a function of frequency. That doesn't happen with the traveling wave tube amplifier. And NRL has recently reported about 30 to 50 watts at over 200 gigahertz in a traveling wave tube amplifier. And there's no solid state equivalent to that. So as a benchmark to shoot for solid state, I have put that on there as the tube on this view graph. Now, where are we going in terms of future trends? Well, I'm going to jump down to the bottom first and talk about semiconductor devices. It's going to be evolutionary. The basic research funding in universities and government labs has gone down in the level of funding that's there. Big corporate labs have disappeared from the scene. So you don't have that basic research that is important to developing new technologies that is funded anymore. So you're not going to see much in the way of revolutionary devices. It's going to be evolutionary, like for instance GaN, which will be pushed to higher and higher frequencies. There are possibilities of some devices that may appear. Diamond shows theoretically it would be a very good thermal conductor and very good electrical characteristics. Make a very good power amplifier as a solid-state semiconductor device. But up until a few years ago, nobody could figure out how to do via holes in there. But now people know how to do via holes in diamond. But no one can figure out how to etch it or dope it still, which is necessary to make a semiconductor device. And because of that, it's still something that may be on the horizon, but a transistor hasn't even been built in it yet. Graphene and carbon nanotube have theoretically shown some promise, but there's significant problems. In particular with purity, there still is a tendency of carbon black structures to find their way into built materials. And you can't have that happen in a semiconductor. There are massive defects that don't allow you to build a large periphery semiconductor. Also, you're not at the point that you can build like single-strand carbon nanotubes. So any FETs that have been built to date on carbon nanotubes is on a mesh, a disorganized mesh of carbon nanotubes. Because of that, your dimensions are very, very large, and you can't get down to the micron-type dimensions that you need for microwave frequency response. So although they show promise, they have a significant way to go before they can realize microwave devices. Boron nitride, some people have said that it may be the next GaN, but still significant development that needs to be done with boron nitride. And then who knows what may appear on the scene. Gallium nitride itself was a bunch of materials people doing research for optoelectronic materials, and they noticed an odd conductivity in a sample. And that was due to the natural 2-degree electron gas caused by the piezoelectric effect. And so that's how GaN got discovered. It wasn't developed as a microwave power device. It just was a happenstance in the material world. So most of the things that are going to be the focus, and you'll see this in the publications, is circuit technique. Everything is going multi-tone for bandwidth efficiency. And the focus will be trading off efficiency versus controlled distortion that's acceptable for the application. So there'll be a continuing effort in the pre-distorters like digital pre-distortion that are on the scene today. And there will be continuous focus for developing towards a simultaneous transmit and receive technique that allows you to reuse some of the bandwidth and get more information capacity through the same bandwidth. Submillimeter wave applications will show up. Submillimeter wave, we have the technology now, but the applications have been slow to develop. Those will start to emerge in imaging and medical and space research. Thermal. DARPA has realized that the GaN and even our digital electronics are thermally limited. So they have started a program that addresses thermal limitations. Some of the programs are shown here. NJTT, which is basically GaN on diamond. Tremendous power density improvements have been demonstrated on that program. Thermal ground plane, which is an alloy heat spreaded. You got to get the heat out of the semiconductor into the next level. iSchool takes that into the next level, into the devices and packaging. Then you get into heat sinks, air exchangers, refrigeration systems using thermoelectric and vapor compression technologies. So that's where I see the trends of the future going in terms of power amplifier development. And this is the final view graph. This is your instructions for if you want a PDF of the presentation. And at this point in time, I'll turn it back to the moderators for questions.
Thank you, James. That was wonderful. So it's now time for our question and answer session. And before we start, just remember that you can still submit questions through the Q&A panel. So let's go on to our first question here. So we had an audience member ask about the cost and efficiency of the amplifiers, especially at high power levels, well above 1 watt of power. Can you make any comments on that?
Well, it really depends on how far you're pushing the power level. Naturally, a 100-watt X-band chip is going to cost more than a 4-watt broadband chip. But, you know, and then there's a question of volumes. Typically, if you're talking onesie, twosies, let's, for instance, talk about that 15-watt KA band chip. If you're talking somebody wants to buy 30 parts, sell price is going to be into the $300, $400 range for those right now. But in volume, that would fall to a tenth of that, if you're talking tens of thousands of units a year. So that sort of shows you the trade that's involved there in terms of volume as a driver for the cost. The other thing is as time goes on, the big driver in cost for GaN right now happens to be the substrate starting cost. And that keeps coming down. People are transitioning to 6-inch from 4-inch, which basically will have the cost of the chip right there. So as time goes on, the cost is going to go down. But again, it's really specific. You have to tell me frequency, power level, and then I can tell you what the various technologies trades are in terms of cost. Okay, great.
So we have a question that's specifically about some numbers on slide 14, and the question is, there are PAEs up to 17%, and the question is this in the linear regime?
The slide number 14. I got to figure out which one of that because we added a few at the beginning as an introduction. Bear with me just a bit.
Okay.
Oh, okay. No, this is at about 3 dB gain compression for those PAEs, and that was usually about optimal for a MESFET technology of those days. That was about peak efficiency because they were gain limited devices. You can see that the gain down at that point is down to the order of 6 dB, and your power added efficiency is going to keel over if you compress it any further. Not quite the case with GaN nowadays. Much higher gain, and typically up to 5 dB compression, you're going to get a slight increase in power and efficiency out of a GaN device.
Okay, great. Here's another question. What are the limits on power for small bandwidth or single frequency oscillator operation?
Ooh, so you talked about oscillators. Could you repeat that question?
Sure, yeah. What are the limits on power for small bandwidth or single frequency oscillator operation? And certainly some of these we can take offline and answer. There's plenty of questions here. So
no, I'll take a stab at it. That I think it really is not the transistor technology that you use, but really can the resonator, whatever frequency determining element that you're using, can it take the power to be able to provide the proper feedback to get oscillation. So I think that would be the determining factor. But I'd also be concerned about the effect of thermal characteristics on the noise of the transistor if you push the power output too far. I think architecturally it would be better to use a low noise oscillator. First of all, bipolars are much better phase noise wise than field effect transistors. and use like a HBT if it's pushing a frequency for the oscillator, even an indium phosphide if you want to go way up with a fundamental oscillator, and follow it by a power amplifier chip. We have characterized GaN, and our GaN Hemp PAs at Ka band showed phase noise performance, residual phase noise, that's additive phase noise due to the amplifier, that was as good or as better as the reference amplifier in the system that had been used for 20 years, an old MESFET design. So you know, the power amps do have good phase noise performance, but I would really go to a low noise transistor like a bipolar for the oscillator itself.
Okay, that sounds great. We have another question here. What is the reason to use a cascode topology for designing HBT-based PAs?
Well, the basic thing is it gives you the gain performance of a 1.5 stage amplifier and the size of a 1 stage amplifier. But also, in most amplifiers that you use, like a common source or common emitter type device, if it's a bipolar, your device is not unilateral. And so changes in your output matching network change your input or interstage matching output network. And that makes it much trickier to get the design centered, especially over bandwidth. When you go to a cascode, it's reduced Miller effect and therefore reduced feedback capacitance across the compound transistor, and therefore less interaction. And that allows you independent matching in those two networks. So it makes it easier to do the circuit design and provide the proper wave shaping technique at the output to get to high efficiency. That said, there's a downside. The second device in cascodes, whether it's a common base in a bipolar or a common gate in a FET type device, is a good oscillator configuration. And so you have to pay a real good attention to stability of the compound transistor.
Okay, appreciate that answer. Here's another question that's specifically about a slide, and it was slide 20. It says, the IMIC on slide 20 looks like it has very wide lines to match to the gate. Is low input impedance still an issue with large GaN parts?
That was just a circuit technique. You know, if you're doing any power amplifier with large periphery, you basically have a very large capacitance with some series inductance which causes phase shift as a function of frequency. And this is just one of the circuit techniques that we use to match the gate side. In this particular case, because the impedances are much higher with the GaN device, we didn't have to resort to that on the drain side. If I push the power amplifier to higher power levels, I'd probably have to go to those type of structures there too. But on the gate side, it just happened to be a convenient circuit technique. I could have also gone to lumped elements and then tried to do a inductive transmission line shunt capacitor technique to implement it. But this happens to be a design technique that was used on the predecessor Hemp amplifier to some success. And so it was just a starting point for the design.
Got it, okay. Another question here. Do you believe there is value in pursuing novel spatial combining techniques at W-band for SSPAs? Definitely.
Spatial, once you get to a large number of channels, is the most efficient way. That basically you've got the loss of free space to do your combining for you. And I didn't have time in this abridged presentation, but in the full DML talk, I show of a spatial combined amplifier that basically has a tapered waveguide at input and output, and has a connector launch that launches to the modes of that tapered waveguide that combines the output of the spatial antennas, dipoles at V-band in that particular case. But it could be any antenna. It could be a broadband thing like a Vivaldi notch. There's a lot of implementations for the antenna. But spatial is definitely one of the ways to go.
Great, and I just want to make a comment that we've got plenty of questions rolling in, and we're definitely not going to have time to answer them today, but we'll attend to those offline, so sorry if we don't get to your question. We do have another one here. Could you comment on linearity optimization techniques in GaN RF Hemps?
Okay, what I have found is that, number one, up until recently, manufacturers have not done anything to address the inherent nonlinearities of the transistor itself. And you find that vendor to vendor, I've characterized a lot of them, that they're all over the map. And to protect the innocent, I won't mention good and bad vendors, but let me say that you can have order of magnitudes difference in whatever nonlinear figure of merit or linearity figure of merit you want to use between the best GaN devices and the worst GaN devices that are out there. So really there is room for optimization. Like most field effect transistors, the principal nonlinearity in a field effect transistor is your transconductance curve. Typically it's a bell-shaped curve for a Hemp, and you're operating off one side of that curve, which gives you asymmetry to the distortion and allows those distortion components to exist. If you could somehow shift the doping profile so that you're at the center of that bell-shaped curve, the even order harmonics would tend to self-compensate for themselves, and you'd only have the odd order to deal with, and deal with those types of distortion and the intermods associated with that. So it's something that there's room at the transistor level to deal with. Most people nowadays just resort to digital pre-distortion for compensation, no matter what the technology is. And one of the reasons for doing that is not only the performance improvement that's attainable in terms of your efficiency distortion compromise, but almost all systems, whether it's radar, comm, EW today, starts or ends with digital IQ. And if you got digital IQ, there's no reason you can't build in a pre-distorted digital IQ transfer function to pre-distort the signal before you feed it to your power amplifier.
Sounds good. Okay, another question here. Looks like there's a handful of questions on the GaN substrates. So do you have any insight into the trade-offs associated with the various GaN substrates? For example, multiple mentions of silicon carbide.
Okay. Silicon carbide is where most of the world has gravitated to. The only other one that's commercially available nowadays is silicon. And people originally did that for cost reasons, not for performance reasons. And there still is a problem with the silicon that the inherent RF performance of the transistor is not quite as good as something like silicon carbide, probably due to lattice and buffer constraints that appear in a silicon-based process that don't appear in a silicon carbide process. Secondarily, the silicon is a thermal limited device. Well, rather, GaN is a thermal limited device, and silicon is not as good as thermal conductivity as silicon carbide. People have tried other things like gallium nitride substrates, but they never really got commercialized. So basically that's your two choices today, silicon carbide and silicon. Silicon, mature technology based on the whole silicon world. Silicon carbide, originally you had problems with micropipes and defects and small wafer sizes, 2-inch, but year after year the basic starting material has improved, where now 6-inch is available with very small amounts of defect, and the cost has come down. So it still really comes down to a performance versus cost trade. For many applications, GaN on silicon might actually be a better choice than silicon LDMOS, where you want to pay a little bit more for performance, but you don't want to go the full Monty and get to a silicon carbide GaN device. So it's a spectrum out there. You'll find everything where there's a market. You'll find parts that are out there, and there are vendors that do GaN on silicon.
Right. Okay. So I think this will be our last question. What is your view on millimeter wave or even sub-millimeter CMOS amplifiers? Is it feasible?
Well, yes, it is feasible. In fact, I'll say that you should look at IMS this year, where a very large CMOS amplifier, and by very large, I'm saying half wattage. But that's something you wouldn't even consider GaN for, but at those frequencies. It's advancing, but I think I'll look to the commercial world to say the difference between silicon CMOS and the compound semiconductors. For many, many years, silicon has been saying they're going to push the compound semiconductors out of wireless front ends, both the switch, the LNA, the power amplifier. And still today, silicon has not done that. So I think it's sort of the wrong niche for silicon, that there's too much of a compromise in terms of performance. And in the cell phone world, battery life is king. People are willing to pay a little bit more for battery life. So if you're slightly more expensive, the cost only at degraded performance argument isn't going to cut it. That same thing works with the LNA and works with the switch in the wireless world. And I think you'll see that in millimeter wave too, in terms of the power amplifier and the LNA and switching. It's just too big of a performance penalty to pay. But let me say this about CMOS silicon. Where it makes a lot of sense is after the front ends, where you can integrate, let's call it all the control function, where you might want to do phase, amplitude, IQ and down conversion, gain blocks, variable gain. That can become a super chip in silicon CMOS, and it makes sense to do those functions in silicon CMOS and not do them in compound semiconductors. So I just think it's a bit of a stretch. Now, that's my personal opinion. There are efforts out there that are funded to develop things in silicon, such as phased arrays, but if you artificially force functions into it, you may need a 10,000 element silicon array to reach the same level of performance of a GaN P-hump front end phased array with a silicon back end in terms of cost and performance. And I'm not sure that 10,000 elements is going to get you to the same cost as 100 elements using more exotic semiconductor technologies.
Wonderful. Wonderful insight there, James. Appreciate that. Okay, so ladies and gentlemen, afraid we're out of time now. We do have a number of questions in the queue, and I believe the presenter will follow up on those unanswered questions offline. So as we said earlier, this session will be archived on the Society website at mtt.org. There's a link available on your view as well. All registrants will get an email reminder with the website address when this is ready for you to download. For attendees that would like to receive the PDH credits, please follow the link in the webcast view and use the code that's available on the last slide that was presented by Dr. Komiak. So once again, I'd like to thank Dr. Komiak for an excellent presentation. Our thanks also go to our sponsor for this webinar, who is National Instruments. And special thanks to our audience for joining us today. We hope you found today's event valuable and that you'll return for future IEEE Microwave Theory and Technique Society webcasts. Have a good day.